Over the past few years, C# has changed a lot, but it feels like the way we write it really hasn't caught up. We have been given immutable data structures and pattern matching, yet our APIs and data structures remain mostly the same. I feel like all this is about to change. But first and foremost, thank you to all the sponsors. Without them, such an open and inclusive event isn't possible. Also, don't forget your sponsor bingo, just maybe after this. Hi, I'm Michael. I'm a full-stack .NET contractor from Perth who spends his days working on web APIs and mobile and brings all sorts of cool things to my team members across Australia and New Zealand. I'd like to see myself as an overly passionate tech nerd who can't really stop getting excited about all things code and hardware. You can find me under the handle Falcomic just about everywhere where I talk mostly about that code and the hardware. I believe that the way we write .NET will change forever. The idea of discriminating unions has been growing in popularity recently, and with key technologies like this, we can unlock closed types, which helps us eliminate an entire class of bugs, as well as a series of standardized built-in types, which remove the need for null and can even guard against runtime exceptions. Before all of that, first we need to look into some of the groundwork the C# team has been putting in over the last few years. Way back in 2017, we got Salt Bay, fidget spinners, but we also got C#7. With this release, the team behind C# gave us some really impactful functional programming concepts. One of those important features happened to be pattern matching. To start out, we have an example here of an animal-based class in which all animals can eat. We also have a dog class, which inherits from the animal class, which has the ability to bark, and cats, which can meow. Now we can see the doAnimalThing method, which takes full advantage of the animals passed in. We can see it uses an isNull expression to make sure the animal was actually provided, followed by a special bark if the type pattern of dog matches. Finally, if the animal wasn't a dog or null, they can have something to eat, as all animals can eat. This is a null match expression, and is basically the equivalent to using an equality check on null. So depending upon your team, you might find that it's better to just keep with what everyone knows. However, you've at least got this as an option. Things get a little bit more interesting when we use the is expression to check for a dog. We can then use a declaration pattern to have a version of that animal as a variable dog, which has had its type narrowed down to a dog. This pattern encapsulates both type checking followed by type casting into a simple and easy to understand assignment that is much harder to get wrong and eliminates an entire type of exceptions that you can get through explicit casting or null errors through as casting. The final else block is only possibility of being a cat. However, because nothing in the C# language specification defines that all inheritors of animal must be exhaustive, it cannot infer the final case. If only there was some sort of union which would allow us to let this be exhaustive. We can at least infer the animal is not null due to the if statement above. Another use of pattern matching through switches, which is definitely one of my favourite ways, is pattern matching. Just like how we used type checking in the previous example, we can do the same inside of a pattern matching switch. We can also use property pattern matching, a technique that allows for more of an expressional approach. In this example, beef would be returned to a dog older than the age of 10 and sausage for those younger as they failed to meet the first expression. Our switch statement also allows us to return a value, which is really handy and allows for tidy and concise code. Pattern matching switches are very similar to the traditional switch in what they offer. However, previously the code was just a touch more verbose. To achieve the same thing, we would have had to write a small essay basically. And there's also the issue that this switch statement can't return any values, which means to set a value, we'd either have to wrap it in a method so that we can return something from the switch, or we would need to mutate a variable defined at the top, both of which aren't practical. Well, they're practical, but they're not optimal. Something still doesn't sit well with me in this example. Once again, we're cursed by the open nature of the class system. To make the compiler happy, we need to supply a default case. We'll find a solution to this shortly, but first, It doesn't feel like that long ago, but I can assume most of you can remember that really big thing that happened in 2020. It kept us inside constantly. We were never sure who to trust, and most importantly, it took over the internet. That's right, Among Us. But I'm also sure that you probably remember that C#9 came out, and with this release, we got another really important feature being records. Records can either be defined in the class style as shown first, or they can be defined in a positional record as shown after. I've added the required and init keywords to the class style to demonstrate how a positional record works under the hood. What this means is if you don't set a property setter to init, technically your record is going to be immutable. So take care when using records and always use init instead of a plain set. Usage of records is mostly the same as a class. However, you won't be able to use the standard set operator. Instead, you'll need to create a new version based off the old one using a with expression. But why would we want immutable data to be passed around? One of the big benefits of a record is that it's easy to understand, and actually you don't have to question what's happening later on. Every time the value is accessed, it will have not changed since you set it, so you know for a fact that the value is going to remain constant. Has this ever happened to you? You're debugging and you've hit a breakpoint. You want to know what the value of some variable was, say, 3 function calls ago. However, the value's been mutated, so now it contains completely irrelevant data and you have no idea what's going on. With records, you can trust your debugger. The value shown in your window will be the value that you need to know. Records are also a great replacement for an ad hoc tuple. You will never need to write string, string, number, object, string ever again. Now, instead, you can name each of those values as a property, with the only cost being a single line definition of that record. This can also help with testing, as tuples can be very hard to near impossible to mock out in some circumstances. And most importantly, it's just too easy to write bugs with mutability. For example, if we had this student class, this is just your average data transport class. Now let's see the main method for this program. First of all, we define a student, which we're trying to authenticate against. Next, we print out the name of the user who is trying to access the database. And finally, we determine whether or not the user is allowed access. The person_exists query method is a pretty simple link query, which checks the database to see if the student passed in matches up with the user in the database, comparing the first and last name. I copied and pasted the first and last name from here to the main method, so I can assure you they do match exactly. Surely, John should have access. So, does John have access? No. But why doesn't John have access? Let's have a closer look at the print name method, which was called right before we checked for access. This is a fairly innocent method. It formats the student name and console logs it. We can also see from the comments that a feature request was made from management to make it such the first and last name are displayed in uppercase. Can you see what went wrong here? If we look at the person_exists query again, maybe you might see the issue. It appears that our database is using case sensitivity, and we just so happen to mutate the first and last name. This example is a bit contrived. However, bugs like this can happen, and the worst part is they'll happen during runtime. It's plain and simple, mutations cause bugs. Why would we continue to program in a way that introduces its own type of runtime errors? If instead of using a class, I have used a record here, instead we would have ended up with this very definition. It is nearly identical to the class I've used, except I've add required where it made sense, and I've of course set all the setters to init. When you swap to using a record, the first 2 lines of the print name method would now get a compiler error, so I've removed them. Through use of the with expression, we're able to clone all the values of the student, including the fact that John loves pizza, but at the same time, we were able to update the student name to a correctly formatted value without changing the original one passed in. So, does John have access? Yes. The print name method has lost its ability to hijack the variable and use it for its own needs. So what did records give us over classes? Immutability was possible previously with classes or structs. However, to do so was a lot of boilerplate, so nobody did it. Also, we can now choose records in the place of tuples, which have barely any boilerplate, but also add a lot more clarity. It's also important not to forget, records give us some really important built-in conveniences, such as iEquality, which allows for automatic equality checking over all the fields inside of the record. Not to mention toString, which does what you would actually expect a console log to do, or a toString to do, and it will print out the values as a JSON in a nice JSON style. That's not even mentioning the with expression, which is quite possibly the easiest way to clone a value and to just update the one or two properties that you need to. Finally, and most importantly, you don't need to worry about your data when using records. When you use a basic mutable class, you pass into your method, you're handing over a liability. You have not defined the contract in which the data is tied to. Working in classes is working in a less strongly typed language. You have not passed along the intent, so that should not be modified. However, if you were to use records everywhere, except for only in special cases, say for example when you're using Entity Framework, then you have very clearly defined a contract that I expect you to modify the value passed in. Basically, why would you leave yourself open to an entire world of bugs when immutability is as easy as using a with expression? Now that we know these new tools and we have these great options available to us, let's have a peek into the future and see what discriminating unions have in store for us. Discriminating unions get themselves confused quite often with regular unions or the one-of pattern, so I think the best way to understand them is that in C# they would be kind of like an enum. For example, if you had an animal enum with 3 values, then we can describe the animal union as having 3 tags: cat, dog, and bird. Discriminating unions I didn't click next, there you go. Where this gets interesting is these tags can also have properties associated with them. The syntax used closely resembles positional records as shown earlier. If I were to convert the dog tag for this example into a class, it would look something like the following. As shown, the dog tag results in what would be equivalent to a regular C# data object with a getter and a setter for the ball color property. If we were to continue this pattern matching example from earlier, the dog tag, once narrowed down, is just as easy to use as the inheritance example was. Some of you might have noticed that I added the class keyword to the enum. That was not a mistake, but a part of the proposed syntax for how you would define a discriminating union. Nothing is really set in stone yet. However, I think it really would be nice if we could use class all record once the proposal moves forward, as it would be nice to also have immutable unions too. But what does this give us? It gives us what is currently holding back a lot of the new pattern matching stuff: a close type. This is a compiler level guarantee that if I have an object of type animal, that it'll either be a dog, a cat, or an animal, and nothing else. If I were to go back into the inheritance pattern matching switch example, but instead were to use the equivalent discriminating union, we can see we can skip the catch-all at the end and have a very happy developer. Finally, we have a close type, and we can remove the catch-all statement, and our switch case is still exhaustive. But why do closed types make me happy? You should probably still be asking that. You shouldn't just trust me. What exactly are we saving ourselves from? If we look at this example of an enum being used inside of a switch statement in which we calculate the maximum age of an animal, we can see that the compiler gives us a friendly warning that our switch statement is non-exhaustive. Luckily, I'm the author of this code, and I know for a fact that an animal must be a dog or a cat, so I can ignore this warning. The only solution I could do for this would be to add the catch-all to the end, but I don't know what I could possibly return for an unknown. -1? I mean, it just doesn't make sense. Why would I support the extra value? Now, if this approach was more realistic, we'd also probably have the request coming in from an API, and of course that would be coming through of JSON. First, we'd have to deserialize the incoming request, and then the deserialized value of animal type could then be passed into the getMaxAge method, and then we could return the result to the caller. We have been working very diligently, and we're now about to release version 2 of the application, in which we add support for birds too. We go ahead and update our animal union to include birds. Now, don't forget to add the new functionality to get MaxAge switch, proving once again we have all that we need, and we don't need the silly catch-all at the end. As the changes are just going live, one of our users creates this request to join using our service. We could expect that they will get a response of 9, as that's what the brand new feature is supposed to return when they pass in a bird. As animal type is 2, that is why I believe this will happen. However, instead, we get a switch expression exception, and it's complained to us that our switch expression has failed to match this input. How could this happen? Little did we know, but the DevOps team has just finished rolling out a new blue-green deployment strategy. What this means is half our cluster is running version 1, half our cluster is running version 2. This has led to our original switch statement, which couldn't handle birds, receiving a value of 2. But why did this reach the switch statement? Shouldn't have it failed to deserialize? No. It turns out the default behavior of JSON convert is that when it sees a number that doesn't fit into an enum, it just puts it in there anyway. So even though our enum could only possibly be 0 or 1, we will still have a 2 in there. Our compiler really was just trying to help us out by letting us know that we were non-exhaustive. With all our options gone, we're forced to take the safer approach. We update our getMaxAge function now to have a catch-all at the end, and we just return -1. Having this catch-all at the end of a switch pattern did solve the easy to miss bug, but it also introduced some new problems. Because there are no guarantees that the enum will always be a cat, a dog, or a bird, we are forced to always handle the unknown. This will end up influencing how we write code, and it will force us to use defensive code paths to account for what really should be an impossibility. The thing is, we've already fixed defensive code paths to a similar problem previously. Open types have a lot in similar to when your project doesn't use nullable. And there's always that possibility the value 1 to 3 properties deep in your class could be null, so you have to check for it. This forces defensive coding patterns, which can lead to numerous null checks in your methods, up in the complexity for about no gain. But as soon as you do have nullability on, all of a sudden, your data structures are what they say they are, and you can trust them. So now you don't need to check null all the way through, because you do the check at the start, and then you can just trust the value moving forward. But how is the exhaustive exception any worse than if we'd have been using discriminating unions and it had failed to parse in the first place? Because it's better to fail early. What if our service costs money? First, we charge the user to access the maxPetAge function, and then we handle the customer complaints when all of a sudden it fails. But if we'd have failed early, we wouldn't have got halfway through the transaction, and we could have avoided doing things that we weren't meant to do. Or even worse, what if we did save the value to -1? Now all of our other services need to know about this, and if they don't, we're going to get data consistency problems. Let's play out another theoretical scenario. What if another team had owned the definition of an animal, and we'd have used code generation in our and used our union to, sorry, 1 second. Let us play out now another theoretical example. What if in this scenario another team owned the definition of animal and we used code generation to generate our union based on the OpenAPI definition? When they update their definition to include bird, our tooling automatically pulls down the new version and generates an updated animal union. What happens? Our application will refuse to build unless this new case is accounted for. Why? Because now our switch statement is not exhaustive. This is okay, and if anything, this is the best possible outcome to a breaking change to in production instead. A breaking build does sound bad and scary, and it's also frustrating that we have to fix something completely unrelated to what we're working on to get our code to compile again. However, I would argue a massive source of bugs in modern C# is developers working in the same domain as somebody else but not respecting each other's work. Sometimes we use coding logic that assumes that we're handling every case, so why not enforce that as an assumption? With all that said, what are some actual examples of unions that are really handy? Option is possibly one of the most impactful unions that would come as a part of a standard library, purely for its conveniences, and would enable library authors to standardize on this one core union concept. Option, to be put simply, is a replacement for nullable types. Instead of using a null reference to describe an optional field, you would use an optional type. Let's use this class for example. Traditionally, you'd have partner being a nullable field. Instead, you could define partner as an optional person. This is very similar to using null with nullability enabled as a part of your project settings. However, it does make your API much more descriptive, and the fact that your property is either a value or not a value goes from being implied convention to laid out in plain black and white. But why would I go to the excess of using option instead of null? If we look at Rust's implementation of this pattern, we can see that by having the lack of value be a type and not a reference, we can extend that functionality, including the functionality of option and its awesome tags. We can define a series of unwrapping methods, including a basic unwrap that throws if the value is null. Then we could simplify this by updating the language to support null forgiving operators, which take the optional person and then makes them into a person, throwing an exception if the value was none, just like the unwrap did. Unwrap isn't limited to just throwing its hands up in the air when the value is none though. We could use unwrap or, which would be an extension method which would either give us the optional value or supply a stand-in replacement. This mirrors up closely to the null conditional operator, and I would assume it would also make it into the language when this came to the standard library. Given we're discussing null conditionals and null forgiveness, we could also then keep the ball rolling and set up the null coalescing operator. Once again, this works almost the same way as the syntax for a nullable type, being that it would wrap the integer in an optional now that we don't know if the value is actually going to be there. In the long run, option is just a null reference with the exception that it is a type and that it contains none or, and some, as well as a tag for defined as tags, whereas null is just a reference. By treating the idea of nullability as a type, we open it up to extensibility that is not tied down by waiting on the language to define these convenience functions for us, just like how we had to wait for the null conditional, coalescing, and all the others. The extension pattern that C# provides us allows us to think of new ways about how we write code and to extend the language freely. And most importantly, it shows intent. I intend this value to be something or nothing, whereas nullability is a marker and more of a legacy workaround and something that doesn't need to exist anymore. Result is another example of something you might think you don't need until you try it. Like option, it is yet another alternative to using null as a marker, however, to signify a failure state. Additionally, it has a hidden and much more valuable alternative use case, and it could fundamentally change how you write .NET forever. In this example, we have a method called read file and count. It is very basic in that it reads a file and then counts how many characters it has. You might assume this method is safe to call. However, little did you know, the true return type of read file and count is int or a lovely read file exception. Unfortunately, it looks like our strongly typed language is actually a loosely typed language. No matter how many docu comments we leave, there will be a time when a developer doesn't realize they should be considering the bad case scenario. Tony Hoare, the inventor of the null reference, has famously referred to null as the billion-dollar mistake. I would argue that in typed languages, exceptions are the trillion-dollar mistake. Languages like C# and Java, or basically any strongly typed language that's old enough to get a beer with us, live their life as a lie, declaring to us that they would accept inputs A, B, or C and return output Y, but in reality throw exception Z. In modern languages such as Zig or Rust, exceptions form a core part of the definition of a method. This means when you're calling a method, you know that you're going to have one of two things occur. Either A, you get the exact result that you were promised, or B, the entire thread will die. And Rust, for example, this is a panic. Panic is not the same as an exception, in that it's used basically to end a thread and when it's reached an unrecoverable state. If you couldn't read a file, you would simply return an error result. My point is simple. Exceptions should be exceptional, not a part of your code flow. So let's say the read file instead returned a result including a string and our read file exception. Then instead of throwing the exception when we handle the read to ends call, we could instead return a typed error. We could even continue to use the exception as the container for this error to help with migrating code. Just please don't throw it. From there, the read file and count would either be forced to handle the error case and maybe return a -1, which would be a common approach, or it could return the result type itself and force the caller to handle the problem. In Rust, this approach of propagating an error up can also be made easy through use of the question mark operator, just like how we use the operators for the option. This works by short-circuiting on the error and returning it back right away, and then allowing us to continue forward with a plain and simple integer. The important thing to take away from a result type is that it is a valid alternative, what boils down to an untyped, exception-driven development. If Microsoft were to update all the standard libraries and NuGet authors were all to move to Rust, to move to Result, billions of dollars of human hours over the lifespan of .NET and all the other languages could be saved, and this would truly change .NET forever. Did you know you don't actually have to wait for unions to be merged into a language? You might have actually been using unions when you used ASP.NET's new minimal APIs. When you start a new .NET API project, you'll be greeted by the weather forecast example, which will be somewhat similar to what's shown here. This endpoint is mapped to a get statement, which uses the weather forecast URL, and will fetch the upcoming weather and return it as an OK200 result. There are some additional Fluent declarations under for the Open API, but that's about it. Out of the box, we have an endpoint which is really nicely documented. We know that we've got an OK result, and that's going to return an array of weather forecasts. To start off, why don't we make it so that we can pass in the time of day? While we're at it, let's make it so that when it's midday, we can encourage our users to go outside and touch some grass by disabling our app. We can do this by returning a bad request when it is midday. Because we return a bad request from the function, now this function returns both an array of weather forecasts and a bad request, so it won't compile. That's okay. We decide to then wrap our weather forecast result in a result.ok, which now our API is happy because both bad request and OK are both implement our result. This looks golden. A new feature is added, so why don't we check out our Swagger docs? I know, it looks like our typed information for our OK result has disappeared. By returning an I result instead of a weather request array, our OpenAPI generator can now no longer figure out what our endpoint is going to return. What's even worse is we don't even document the fact that it could return a 400. This is an easy fix. We can simply chain a call to produces 400 and produces weather forecast array with a 200 status code. If we give this a run, we should see our Swagger doc information is coming up correctly, which it does. If we put in a 12, we get our 400 result, and if we put in any number, let's just say 3, then we should get an array of temperatures. Oh, it appears I've made a mistake. I accidentally documented that the endpoint will be returning an array of integers, but in actuality, it returns an array of weather forecast. This is a mistake is just as common and just as easy to make inside of the traditional controller-based approach. If another team had have used our OpenAPI definition to generate a client, this likely would have been found pretty quickly, but what if the mistake was more subtle and just never got found for us in production? If only there was a way we could use C#'s type system to enforce our OpenAPI contract. Fancy you say that. There just so happens to be a way, and it's called typed results. First of all, let's remove the two producers. Next, let's define a return type for the weather forecast to, instead of being inferred, we'll hard-code this to be the result generic class, which acts kind of like a union in which it's made up of cases, and this one being OK weather forecast array and also bad request. Then all that remains is to change the results helper class to instead be a typed results helper class. Now, if we were to run this application again and look at the output, you'll see that both the 200 and 400 are documented, and the correct type information is supplied automatically. If we go back into this example and say, for example, instead of returning bad request when it's midday, we return not found, you'll notice that we get a compiler error. Or if I'd have gone into the OK result and changed it to be an array of integers, once again, we'll get a compiler error. This is an example of how the minimal API's result generic is emulating a constrained union and can only contain one or more different types of iResult possibilities. Under the hood, the result class defines an implicit cast operator for each of the possible result types, for example, OK and bad request. If we fill in these blanks to form from our example, it'll look like this. Now, our weather API endpoint returns a type result of OK, and we call our implicit operator, which accepts the OK and then wraps it in the strongly typed result containing both OK and bad request. From this, the Open API middleware can use reflection to accurately grab the possible results its endpoint can return. What we just saw there was an implementation of the one-of pattern. The one-of pattern is more of a user-land way of representing unions. Recently, an implementation of a union library has actually been on the rise. Specifically, it's an implementation of a discriminating unions. The API that dotnet provides includes a match method, which at compile time enforces that all possible outcomes are covered, plus other convenience functions to access individual types. In dotnet, you must provide your type ahead of time through the use of a source generator that will allow you to attach to your partial record through the use of the union attribute. As we can see in this example, this implements the well-known option union. dotnet allows method called match to be used. dotnet allows us to use a method called match against our union. This method enforces that all the tags of our union have a function expression supplied. If I were to remove the none function, I would get an error, or if maybe I would add the maybe tag, I would also get a failure to build. What makes this truly powerful is that dotnet supports serialization, so we can use discriminating unions inside of our contract layer between dependent services. Even though dotnet is missing true pattern matching, in which we could have multiple functions for multiple patterns, it still does do the core thing, which is to give us the option to make sure we don't miss any of our possible tags. I really do feel like it does provide enough value to be worth using. Especially with out-of-the-box support for serialization, I would definitely consider this library moving forward if it matched up to my team's needs and willingness to take on a risk. I could very well see myself using dotnet to generate the response type for my mediated contract layers. This would allow for a safe amount of usage to what in the end is still a new library, but in the end my eventual goal would be to replace it with official discriminating unions when they arrive. But where does this leave us all? As it currently stands, if you want to use unions, you have no option but to emulate them through libraries. Sure, dotnet does allow us to match against all possibilities and to account for otherwise a compiler error. However, we cannot use proper pattern matching, which is a major downside of one of the key benefits of pattern matching, is that it allows us to one of the major benefits of regular pattern matching is that not all logical actions we take are shaped just by the type. Sometimes sub-properties are important. I try to reassure myself that we will have closed types in C# soon. But the sticking point here is the proposal has been for championing discriminating unions has always felt like one release away. But we are now 5 major versions of C#, 7 years and 785 comments into the proposal. We are finally starting to see Microsoft use union-style patterns in major ways, but there's still no known release point. The only real positive thing I can take away from this is that I really have picked a winner when it comes to a presentation idea. I could very well milk this for years. Try not to get bogged down by all that. What are some of the good things that have come to C# but are not being used to its full potential? Records make immutable data viable and a great solution. With handy tools like with expressions and literally the most simple possible APIs, it's easy to create immutable data structures and use them, and it's just about as much work as mutable ones. Even if we don't have closed types, pattern matching allows us to remove heaps of code and form much more succinct programs. Want to perform an action when the type is null and a property value is a certain condition? Easy. Just use some curly brackets, and without having to check for null and change some Boolean logic, you get exactly what you want. We may not have all the tools at our disposal that pattern matching allows, but it's still a great solution for what we do have now. With all of what we currently have, especially when we do get discriminating unions. But in the future, I really do see us fundamentally changing how we write code forever.